In section 6.7, we're going to explore the use of enthalpy values from reactions to predict the enthalpy changes of other reactions using Hess's law. We'll do this by sketching energy diagrams using thermochemical equations and by modifying equations and predicting the effect on the enthalpy. Let's begin. The heat, or enthalpy, associated with chemical reactions is measured using calorimetry and the equation Q equals MCAT. That means the heat absorbed by the surroundings will have the opposite sign of heat than the reaction, because we always take the perspective of the system. Once we know the heat absorbed or given off by a reaction, it's customary to report it in kilojoules per mole of reactant used or product produced. You'll often see this value included after a thermochemical reaction. Suppose we're given the reaction 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. We could report this reaction as negative 572 kilojoules per mole of oxygen used, but we must write the equation with coefficients of 1 in front of the water if we'd like to report heat given off per mole of water. To accomplish this, we divide the coefficients by 2, giving us H2 plus 1/2 mole O2 yields 1 mole of H2O. Enthalpy is an intensive process, meaning it depends on the amount of substance present. So if we use fewer reactants, less heat will be produced. We adjust for this by dividing the enthalpy value by 2 as well. We can also determine how much heat is produced when 3.30 moles of methane is combusted according to the balanced chemical equation. Assuming we have excess oxygen, we start with what we're given, use 1 mole of methane is equal to negative 891 kilojoules of heat produced as a conversion factor, and get 2,940 kilojoules. What if we're asked to determine the enthalpy for the equation here? All of the coefficients have been doubled, so we must multiply the enthalpy value by 2 as well to get negative 1,780 kilojoules. Enthalpy change is defined as the heat transfer for a process carried out at constant pressure. Because enthalpy is a state function, its value does not depend on the history of the system or how it got from point A to point B. Instead, the enthalpy of a reaction depends only on the identity of the reactants and the products, not the individual steps it took to convert the reactants to products. In future classes, you'll learn more about the enthalpies for specific processes, such as the enthalpy of solution, which describes the heat transfer associated with a solid dissolving in a solvent, the heat of fusion, which is more commonly known as melting, and the heat of vaporization. For now, let's keep working on the enthalpy of reaction until we have a firm grasp of all the ways this value can be used. Suppose you're interested in trying to develop a new reaction. You might be tempted to go directly to the lab to try it out, or if you do a bit of research, finding a way to estimate the enthalpy of reaction prior to beginning will increase your odds of success. Or you might find the enthalpy changes for a reaction are difficult to measure directly. Regardless, Hess's law allows you to calculate enthalpy values using the enthalpy of a series of related equations. As we'll see in a moment, when chemical equations are added together to yield a different chemical equation, the corresponding delta H values are added to get the delta H for the desired equation. The first rule of manipulating thermochemical equations tells us that if an equation is reversed, the sign of the enthalpy change must also be reversed. If you think about it, this makes sense. As written, the first equation is telling us that heat is absorbed by the system. This is an endothermic reaction, which would feel cold to the touch if you were to put your hands on the flask containing the reaction. If we could run this reaction in reverse, rather than heat being absorbed, heat would be given off. So keep this in mind. Reversing a reaction flips the sign on enthalpy. We've already used our next rule, but it bears repeating. If the coefficients in an equation are multiplied or divided by a factor, the enthalpy value must be multiplied or divided by that same factor. Enthalpy depends on the amount of reactants and products present, so doubling the reactants will double the amount of heat released, as shown in this example. Our third rule, which is at the heart of Hess's law, allows us to add two reactions together with their associated enthalpy values. When we add the reaction of diamond with oxygen to produce carbon dioxide, with the formation of graphite and oxygen from carbon dioxide, whichever species show up the same on both the reactant and product sides will cancel out. What we're left with is the process that allows for diamond to turn into graphite, which gives off a small amount of heat. Here's another example. Suppose we need to calculate delta H for carbon plus oxygen yields carbon monoxide, but all we have are the enthalpy values for the two thermochemical equations given. How do we go about solving this? First, we note that 1 mole of carbon needs to be on the reactant side, 1 mole of carbon monoxide needs to be on the product side, and however we add these two equations together, we eventually need 1/2 mole of oxygen to show up on the reactant side. The first reaction has 1 mole of carbon on the reactant side, so we're going to leave it alone. The second reaction has 1 mole of carbon monoxide on the reactant side, so we need to reverse that reaction. When we do so, we must also change the sign to get this reaction. Adding the two reactions together, carbon dioxide will cancel out, 1/2 mole of oxygen will cancel out, and we get carbon solid plus oxygen gas yields CO gas. Delta H overall will be negative 393 kilojoules plus positive 283 kilojoules equals negative 110 kilojoules. Since the sign of delta H is negative, this tells us the reaction is exothermic overall. Now, continuing to work with this reaction, we can also graph it as follows. We can show the first reaction as starting from high energy, then losing energy, as diagrammed with the downward arrow. This means heat is being given off. The second reaction was endothermic, meaning energy is absorbed by the system, as diagrammed with the upwards arrow. Overall, the energy gap shown tells us that heat is given off by the reaction. We'll see more examples of this in the next lecture. Here's one for you to try. As always, I'll leave you with the parting thoughts of the authors.